Cool. So we're going to go right in here. We got a lot to cover in this course. In general, it's just material that is kind of dense that we have to go through. I'm not trying to be mean by making a super hard course. What Organic Chemistry 1 is set by the state of California, and that's nice because then it transfers to all these other colleges and stuff like that, but we got to get through that material, all right? So we're going to dive right in here with a pretty natural place to start. Or non-organic chem? Okay. Okay. Pretty natural place here would be, what is organic chemistry? And I am going to, just FYI, I'm going to use this whiteboard or this projector kind of the whole time because I'm recording our lectures as well, and I want to be able to post that. As much as I love working on whiteboards and board work, I think it's more beneficial to have it down and have a video of that sort of thing. So make sure that you are in good view of our projector here. That's sort of exclusively what I'm going to be doing our lecture notes on. All right? So first of all, introduction to organic chemistry. Okay, so just sort of a historical little tidbit of fun fact here. Where does this organic versus inorganic chemistry come from? It kind of has deep roots that go way back to kind of the beginning of chemistry, right? I mean, science wasn't really always a way in which human beings were thinking. For a very long time, everything was very religious-based in terms of our understanding of the world around us. Then we had that scientific revolution, and scientists, chemists had one gigantic success, which is why we all study chemistry, and that is sort of establishing that the world around us is made up of atoms, right? All these atoms and stuff like that. So that was a very early win for chemists. That's the basis of chemistry, right? So where did organic chemistry come from? Well, still for a very long time, they thought that human beings were special. We were made of different stuff than the world around us was, right? It was still sort of this kind of, had roots in religion, this idea that like human beings are sort of divine and that sort of stuff. So for a very long time, we thought that what we were made out of, even if we were made out of atoms, was different from the rest of the atoms in the world around us, in the dirt and all that sort of jazz, right? And then, all of a sudden, a scientist, a very early chemist, established that actually I can turn dirt and rock and oxygen, all those elements that I get from that, and I can make a molecule that's found in the human body. They have sort of been studying this molecule called urea, which is found in urine, fun enough. But they had established sort of properties of this molecule, and then somebody went along and synthesized it on their own. So all of a sudden it was like, oh, game's changed. Actually, what we're made of could be understood in the same way as all the other elements. But that's why this sort of separate branch of organic chemistry exists. It's specifically studying organic matter, okay? The stuff that we human beings are made of. And it does sort of help to differentiate these things, because organic molecules are very different than, say, inorganic molecules, rocks and stuff like that. In two major ways. So first of all, an organic molecule necessarily contains two elements. Okay, does anybody know what one of them is? Carbon, right? Has to be carbon to be an organic molecule. Okay, and the other one is hydrogen. So organic molecules are molecules that necessarily contain these two elements. Okay? Now, because of that, does anybody know, let's remember, looking at our periodic table here, what lives on this side, the metals or the non-metals? The metals are over here. The non-metals are carbon, and actually hydrogen's kind of a weird spot, right? It's also a non-metal. So all of our organic molecules are based in these non-metals. And what type of bonds do non-metals have? Ionic or covalent? Covalent bonds, okay? So organic molecules are carbon and hydrogen, and very importantly, their bonds are all covalent bonds. Covalent molecules in general are just way more freaking complicated than ionic compounds. Ionic compounds, because of that distribution of charges, the fact that one's positive and one's negative, it just makes those interactions way more straightforward. Covalent bonds, where electrons are being shared, it's just like a way more complicated sort of thing. And so that's why it's really helpful to study organic molecules, really the study of these covalent molecules separate from rocks and ionic compounds. Okay, so that's why our branch of organic chemistry exists. And yes, so we're going to be studying a whole bunch of carbon and hydrogen containing compounds. Okay? And let me just give you a preview of how this sort of first few weeks is going to work. The very first thing that we're going to do is like lay some groundwork and build our tool chest of how we can talk about organic chemistry. All right? Like, I mean, I don't know, if you've ever like read Harry Potter or something, right? You understand something about that character based on these sentences that you're reading, but you had to start with learning the alphabet. Right? You had to start with putting these sentences together. And so that's kind of where we're going to have to do is we're going to have to start with a sort of way of looking at molecules and stuff like that where we can understand what's going on in these pictures. I mean, by the end of it, I'm going to be talking about pentane, and I'm going to put down something like this, and you're going to know exactly what the heck that squiggly line means. Okay? That's kind of what we got to do is first learn about these things. And that's because where we're going to start is sort of the thing that's very important in organic chemistry, and that is the structures of molecules. All right? We almost do no math in this course, which I know to a lot of people is like, man, awesome, and other people are like, crap, that's how I got through, all right? I was a math kid, so this was a little bit of a rough one for me. But we're gonna do almost no math, but we are gonna be drawing a lot of pictures. We're gonna be drawing a lot of structures, and those are gonna mean something, right? That's how we're gonna understand organic chemistry. So we gotta start with these structures. The first thing we're gonna do is review what you guys have already learned about structures, all right? And those are what we call Lewis structures. Now, Lewis structures, they convey all the structural information that we want in organic chemistry, but they're kind of a pain in the butt to draw. They take way longer than that little squiggly line that I wrote, right? So we're gonna start with Lewis structures because that's what we know. There's a lot of explicit information there. And then by the end of this week, we're gonna have gravitated towards those squiggly lines, okay? But first thing we gotta do is review what we should know about Lewis structures. So the first thing I want everybody to do is to draw me the Lewis structure of good old faithful water molecule. All right, draw me the Lewis structures. See what you can remember from your past chemistry courses. What the heck I'm even talking about with the Lewis structure. All right, but what does a water molecule look like here? All right, so the Lewis structure is where we have H and then a line, oxygen, then a line, and there's 2 dots on those oxygen, actually 4 dots, I guess, total on the oxygen. All right, so let's remind, I know everybody got this first try, knows exactly what they're looking at, but just in case we need to review a little bit, let's make sure that we understand what's going on in this picture here. All right, so these lines, they represent covalent bonds. Right? Those are what our sticks represent. So this is representing a bond between the oxygen atom and the hydrogen atom. And how many electrons make up a covalent bond? 2. Right? So that stick represents a pair of electrons. A pair of what we call bonding electrons, or just more simply bonds, right? But remember, those sticks represent a pair of electrons, and that is a bonding pair of electrons that's shared between, in this case, the oxygen atom and the hydrogen atom. That's what's holding them together. Cool? All right, so then these little dots, these are electrons that are non-bonding electrons, right? Does anybody remember what we call these? Lone pairs. Those are also 2 electrons, okay? The difference is these are not bonding electrons. They are only associated with that oxygen atom. They're not being shared between 2 atoms. They are plopped right on top of just that one oxygen atom, okay? Now, in general chemistry, when you were taught how to draw Lewis structures, you sort of were taught how to count the number of valence electrons, put something in the middle, put the other ones around it, and you're like always keeping track of how many electrons you have and how many are on the board, right? That was the name of the game. Because in organic chemistry, we're limiting ourselves to such a few elements, right? Just that one sort of, generally speaking, carbon and hydrogen, right? They're going to be in all of our organic molecules. The other elements we're going to see a bunch of are oxygen, nitrogen, maybe the halogens, fluorine, all right? But generally speaking, just that one row. Because of that, what we're going to do is we're going to create a little bit of a simpler set of rules for drawing our Lewis structures, and it's going to work for all of our organic molecules here, okay? So we're going to make a little chart here. We're going to put the elements, hydrogen, carbon, nitrogen, oxygen, and fluorine up at the top. All right, and then on the side, we're going to keep track of how many valence electrons each of these elements has, how many electrons they need for a full octet, that octet rule. Oh, crap. Don't disobey me, computer. Okay. Our octet rule. And then we're going to keep track of the number of bonds each element likes to have. And then the number of lone pairs. So it turns out that in every organic structure that you see, carbon will have the same number of bonds and the same number of lone pairs, right? So we can just sort of simplify this. Rather than having to calculate, do all this math for our Lewis structures, we're just going to draw based on these rules here. So let's fill in these first two columns first, because they're just kind of review of some terminology. Does anybody remember how many valence electrons a hydrogen atom has? 1, right? So they're based on the column number here. Everything in this first column here has 1 valence electron. Everything in the second column here has how many valence electrons? 2, all right? But then we skip the transition metals and we pick it back up here. How many valence electrons in this column? 3, 4 for carbon, 5 for nitrogen, 6 for oxygen, 7 for fluorine, and 8 for our noble gases. There's kind of one pain in the butt exception, and that's helium. It's kind of in the wrong column. It's a noble gas, but it doesn't have 8 valence electrons. It's too tiny. It only has 2. Okay? But for these here, so for hydrogen, whoops, can't write there, we have 1 valence electron. For carbon, we said we had 4. How many for nitrogen? 5. Oxygen 6, and fluorine is 7. Okay? Now, remember, when you learned about molecules forming bonds in the first place, why do they form bonds? Because they all want to fill their valence shell, what we call the octet rule, right? Everybody's trying to be like a noble gas and have a full valence shell. So the octet rule is a little bit of a misnomer, but it's a helpful way to say it because for most of the elements up here, how many electrons do they need to fill their valence shell? 8. That's why it's the octet rule, right? And this is true for all of our elements starting with carbon, anything larger than carbon. So carbon, nitrogen, oxygen, and fluorine all want 8 electrons to fill their octet, okay? But it is a little bit of a misnomer in the sense that there are some elements that want fewer than 8. Hydrogen is the one because, again, all organic molecules contain carbon and hydrogen, right? So hydrogen is going to be the one that we want to pay extra special attention to. How many electrons does hydrogen need to fill its valence? Does anybody remember? Yeah, just 2, right? It's just so teeny tiny, it can only hold 2 electrons. Okay? Other notable exceptions would be beryllium. At the very top, also teeny tiny, can only fit 4 electrons. All right, and boron can only fit 6. These are very random exceptions that we will see very, very seldom, but just something to keep in mind, something that we should know from general chemistry. All right. Okay, so now is where the really helpful information is going to come here. All we got to do when we look at a structure is make sure every element has the correct number of bonds and the correct number of lone pairs. All right, so for each one, hydrogen, again, so teeny tiny, will always only have 1 bond. There is no such thing as a hydrogen with 2 bonds, and no lone pairs. Okay. Carbon, how many bonds does carbon like? Not 2, 4. Carbon loves 4 bonds. 4 bonds and no lone pairs. And that is a pretty hard, fast rule. There has been like one discovery very recently of a compound where carbon had 5 bonds, but it is super extra special case scenario, doesn't exist but for 2 seconds in a lab somewhere, not any sort of problem that we're going to have to deal with. As far as we're concerned, carbon has 4 bonds and no lone pairs, right? That's what a carbon atom likes to have. When we get to nitrogen, nitrogen likes to have 3 bonds and 1 lone pair, okay? Something like an ammonia molecule, for example, NH3, right? 3 bonds and 1 lone pair on that nitrogen atom. Oxygen, like in our water molecule, had how many bonds? 2. And how many lone pairs? 2. All right, and then fluorine likes to have just 1 bond, much like a hydrogen atom. All right, the difference is that it's surrounded by a ton of lone pairs. So a fluorine atom has 3 lone pairs. All right, and I just want to point out, I sort of organized these just how they're organized on the periodic table. Look what happens to our number of bonds as we go across our periodic table. Carbon likes 4, nitrogen likes 3, oxygen likes 2, fluorine likes 1. And then if we look at our lone pairs, it's doing the exact opposite. Carbon has 0, nitrogen has 1, oxygen has 2, fluorine has 3, right? So they're not like kind of random numbers out in space. There's this trend that's associated with them that you can look for if you forget. All right. So now we're going to use this, our little cheat sheet here, and we're going to start drawing some molecules, some Lewis structures of molecules that are too big for your simple Gen Chem 1 set of rules to work for, right? Those only worked for simple atoms that have this one central atom. We're not only going to be talking about teeny tiny atoms, right? We need to talk about the big stuff too. So using this set of rules, let's try to keep it on here. I want everybody to take a second and draw me a molecule with the formula C3H8. Start sticking stuff together, trial and error, in such a way that you make sure all your carbons have 4 bonds and all your hydrogens only have 1 bond, right? According to our little cheat sheet of rules here. And I might give you a hint that's going to work for, in general, when you're drawing molecules. Save those hydrogens for the end. All right? They only got the 1 bond. They're kind of going to decorate the outside. So put your carbons down first, and then decorate them with the hydrogens afterwards. All right. Actually, I need to... Cool. All right, so I'm going to start by putting my carbons down. I need 1, 2, 3 carbons. All right, and then I'm going to decorate them with these hydrogens, and I'm just going to put as many hydrogens down as I need to make those 4 bonds for carbon. All right, so let's look at this one here. How many hydrogens should I put on that green carbon? 3, right, to make it a total of 4 bonds. Same thing for this one on the end here. It also needs 3. Boom. And then how many on that middle carbon? 2. Just 2, right? And if you did this the long way and you totaled up the valence electrons and all that jazz, it would all work out, right? But we can make it a little bit easier for ourselves because we're always talking about the same few elements. Just make sure you have the correct number of bonds and the correct number of lone pairs. All right, and this is something that may be a little weird at first, and by the end of this semester, you're going to have drawn so many freaking organic molecules that it's just going to come naturally how many bonds everything should have. All right? So let's do another one. So now you're going to give me something with the formula C2H6 Oh, we're going to throw an oxygen in there. All right, so again, I'm going to save those hydrogens for last, right? We can decorate everything with our hydrogens at the end here. So I'm going to put down a carbon, another carbon, and then my oxygen. All right, I need to make sure that everything has the correct number of bonds. So this carbon should have 1, 2, 3 hydrogens. This carbon should have 1, 2 hydrogens. And where's my last hydrogen going to go? So I have a total of 6, like my formula here, on the oxygen, right? Oxygen needs 2 bonds, and then I'm done? No, the lone pairs. Don't forget about the lone pairs. It turns out that especially when we're talking about reactions, those lone pairs are super duper important, right? So make sure that you understand that this oxygen not only has 2 bonds, but also has these 2 lone pairs sitting on it, okay?
So is that the only way you can draw?
No, there's one more actually. There would have been one more structure that you could have done that would have been completely fine. It wouldn't have broken any rules. And that would have been to simply put the oxygen in the middle, just kind of rearranging what you have here, right? Then each carbon would need 3. How many hydrogens should I put on that oxygen now? None, right? Because it's already got its 2 bonds. I do need to put 2 lone pairs on there though. And then 1 more. All right, so we'll see, and this is why drawing out these structures is so important in organic chemistry, because those formulas really don't tell you all that much information. They could be pointing to more than one molecule. In fact, the more carbons you have in a formula, the more different molecules you could be talking about. Okay? So in this case, yes, there would have been these 2 perfectly legal structures that you could have done for this formula here. And again, we're just doing this by our rules, right? Carbon has 4 bonds, hydrogen has 1 bond, and now we have to remember oxygen has 2 bonds and 2 lone pairs.
Will we need to be caring about like resonance structures class or no?
We will get to resonance next week. All right, we're going to start with our simple structures first. All right, so now let's do another one. Let's do C2H4O. All right, we're going to 2 fewer hydrogens in this formula here. What you're going to find is that you sort of run out of atoms here and you don't have everybody's rules satisfied. All right, the way you're going to get around that is you're going to need to have a double bond in that molecule. So everything we've been doing thus far were only single bonds. You're going to have a double bond in that molecule. So see if you can remember what those look like. All right, so if I put down my backbone here, my carbons and oxygens, 1, 2, 3, and let me just sort of show you what I mean by you run out of bonds here. I'm going to put on my hydrogens 1, 2, 3, 4. My carbon's mad and my oxygen's mad, right? I haven't met my rules yet. So how we can get around this is with a double bond to that oxygen. And then, of course, we need those 2 lone pairs. Just like the other one, there would be another what's called structural isomer that we could have done, and that is to put our double bond between our carbons instead. Now decorate with the hydrogens. And this time I would need to put that 4th one on my oxygen. Okay, so let's not forget double bonds also exist. If we have a double bond, how many electrons are being shared between those 2 atoms? 4, right? Each bar, each stick still represents 2, but we just draw 2 lines for a double bond. All right? There's something else that's we're going to talk about with double bonds that, to be quite honest, I don't remember if you talked about in general chemistry or not, but that is whether these are whether we're talking about a sigma bond or a pi bond. For right now, we just need to be able to recognize if there is a pi bond or if there isn't a pi bond. We're going to talk a lot about pi bonds as we go further in the course. For right now, what we need to know is that all single bonds are just what are called sigma bonds, right? So I got a whole bunch of sigma bonds. When we get to a double bond, one of them is a sigma, the other one is what we call a pi bond. We're going to see these pi bonds are pretty special. So one of them's a sigma, one of them's a pi. Whichever one you designate it, it doesn't matter. There's not like a rule where the top one has to be a sigma bond or something like that. Just you have to know that a double bond is made up of 1 sigma bond and 1 pi bond. All right. And the last one you're going to do for me is C2Cl2. So first of all, what the heck do I mean by Cl? Chlorine. But let's look at our cheat sheet here. I don't have any chlorine, so how am I supposed to know what that one does? Where am I going to look? It's a halogen, right? So remember, why the periodic table is grouped the way it does is because elements that live in the same column, they behave very similarly. So all these rules that we established for fluorine, they work for every single halogen in that column, right? Same thing if I asked you about sulfur, where would you look on this little cheat sheet table? Oxygen, same exact thing, right? 2 bonds, 2 lone pairs, because they live in that same column. All right, so fluorine is where I'm going to look. My chlorine wants to have 1 bond and 3 lone pairs. All right, so C2Cl2. Those chlorines are like hydrogens. They only have 1 bond, so put it last, right? Save them till the end. All right, I'll give you a hint. A double bond is just not going to do it. You need to go 1 more to a triple bond in order to make this molecule work. So my carbons are going to have to be triple bonded together, and then my chlorines will be sticking out on either side. Remember those halogens, they got a ton of lone pairs on them, so I'm going to have to put 3 lone pairs on each of those chlorine atoms. Okay, again, the lone pairs are really important. Don't forget them, easy mistake to make. All right, and then just for completeness, let's do one with a nitrogen atom as well. So we'll do CH5N. All right, so again, I'm going to save my hydrogens to the end, connect my carbon and my nitrogen, and then I'm going to go back, make sure that my carbon has 4 bonds. So 3, and then how many on my nitrogen? 2. So that my nitrogen has 5 bonds, and then I'm done. No. I got to put that lone pair on my nitrogen. Okay. The other thing I just want to sort of point out with regard to Lewis structures is you would sometimes see kind of this same thing, but maybe with the hydrogens pointed in those directions like that. It really doesn't matter, like the spatial orientation of things. It matters how many bonds everything has, how they're connected, how many lone pairs it has, right? I could put the hydrogen on the top, I could put it on the side, I could put it on the bottom. The spatial orientation is irrelevant, okay? And the reason you might see it drawn sort of like this is because it gives you a little bit of a hint about the geometry of that structure, which is the next thing that we're going to review here, right? You first learned how to draw these Lewis structures, and then you learned how to look at them and count bonds and count lone pairs, and from there you could figure out what the geometry of those structures were, all right? So let's review that. So, geometry and hybridization. I don't remember how to spell. Okay. So the way that you did this is the first thing you did is you learned how to look at a Lewis structure and count how many electron regions there were about a particular atom. So let's just remind ourselves. An electron region is a bond of any order. So double bond, single bond, triple bond, all is just one electron region, and lone pairs. Okay, now, previously when you discussed geometry and stuff like that, you were always looking at very simple molecules. For more complicated molecules, it turns out that each atom has a specified geometry. So I'm going to tell you what atom to look about. We're going to go back to these structures that we drew before. Let's go back to this very first one, and let's look about this particular carbon atom here. And we need to count how many electron regions we see about that carbon atom, right? So again, if a bond of any order is one electron region, how many electron regions are about that carbon? 4, right? 1, 2, 3, 4. Okay. So from this, we were able to interpret what our geometry is. So again, we're going to make a little cheat sheet table here. We're going to put number of electron regions in one column, what we call the hybridization in the next column. And then these correspond to what's called an electron geometry. Okay, so first of all, hybridization. If you remember from elements, you learned that based on the periodic table, carbon has electrons that are 1s2, 2s2, 2p2, right? Those are if you had a single carbon atom. When you go and you make bonds, those S's and P's, they mix together to form new what are called hybrid orbitals. Okay? So by the number of electron regions, okay, we got 3 options. There's always going to be either 2, 3, or 4 electron regions, like what we just saw in our previous molecule. Okay? Whoops. Number of electron regions. If you have 2 electron regions, then you have an sp hybridized orbital. 1 s mixed with 1 p to make this new hybrid orbital where the bonding electrons live. All right? That electron geometry is what we would call linear. If there's 3, then it's an s and 2p orbitals, what we call an sp2 hybridization. And these will produce trigonal planar electron geometries. All right, and then lastly, our 4 electron regions correspond to an sp3 hybridized atom, which has this fancy schmancy name, a tetrahedral geometry. All right. In the lab portion of this course, we're also going to be talking about structures, and one of our activities that we'll be doing later in the week will be building these structures with those model kits. If you looked on the bookstore website, you would have seen that these model kits are up there as like an optional sort of thing. I loved my model kit when I was in organic chemistry. We're going to start talking about something called stereochemistry a little bit later in the course, where I feel like a model kit is really essential to kind of like drive home, because you're going to be spinning these molecules around. It's just really helpful to have that sort of like tactile whatever. If you don't want to get a model kit yourself, we do have them here. All right, and one of the things I discuss in my syllabus video is that every Friday from 8 a.m. to 2 p.m. we have what's called GRASP in this room, where there's always a chemistry faculty member here, and you can do stuff like borrow computers or check out a model kit or something like that that you could then practice with, okay? So if you don't want to get one yourself, I understand, but know that we have them here, and know that especially for certain parts of the course, they're very, very helpful in sort of like getting your brain to wrap itself around certain information, all right? Okay, cool. So we said that this carbon atom had 4 electron regions. So that means what's its hybridization? sp3, which means that it has an electron geometry that is a tetrahedral. Okay? Now, we have this other cheat sheet, and I will post my lecture slides at the end of the week so you guys can have this little table in here. I just grabbed it from an old textbook, but it kind of nicely summarizes things. We said 4 electron regions, they call it electron groups, same thing, all right? That corresponds to that tetrahedral electron geometry, all right? So if we just want to zoom in here, this is what a tetrahedral looks like. This is actually how you would orient 4 things in space so that they're all equally spaced apart, is in this tetrahedral shape. It's a very strong shape. Diamonds are made of tetrahedrally linked carbons. But yes, so that is that shape there. And in the case of our molecule that we were looking at, there were no lone pairs on that central atom, right? If there are no lone pairs, then the geometry of the molecule is just the same as the geometry of the electron geometry. So it would also be a tetrahedral. Okay? The bond angle on a tetrahedral, that magic number is 109.5. That's how far apart all those atoms are in space. All right, let's do another one. Let's go to our nitrogen-containing compound, and let's look about that nitrogen in the middle there. Oh, not in the middle, on the end. All right. How many electron regions do we count for this guy? 4. Awesome, right? Because each bond counts, but also a lone pair is an electron region. All right, so 1, 2, 3, 4. So what's its hybridization? That sp3. And its electron geometry would be a tetrahedral, right? Including the electron geometries, including that lone pair, all right? But if we talk about our molecular geometry, lone pairs are like invisible, right? You can't see a lone pair when you're looking at a molecule. So if we have these 4 electron regions, we have that tetrahedral electron geometry, But now one of those bonds is actually taken up by a lone pair. So we call that geometry with that lone pair on there trigonal pyramidal. It forms like a little squat pyramid on the table. All right? And so you will see this often with nitrogen, right? Because nitrogen likes to have 3 bonds and 1 lone pair. So nitrogens often adopt this trigonal pyramidal geometry. All right, and then let's go up here to our oxygen-containing compound. And let's look about this oxygen. How many electron regions does it have? 4, right? Because those lone pairs count. So it's sp3. And again, that means its electron geometry is tetrahedral. But now I got 2 lone pairs in the place of my bonds. Does anybody remember the very fancy name we have for this geometry? Bent, yes. I don't know why. All the other ones are these like elaborate Latin words, and then they got to like oxygen. Yeah, it's bent. I don't know. So yes, these are bent geometries here. And again, similar, we see these patterns from the periodic table. Because oxygen likes to have 2 bonds and 2 lone pairs, you will often find your oxygen in a bent geometry. All right, now let's go up to our double bond compound here. We'll do this one here. Really doesn't matter if you would look at the oxygen double bonded or the carbon, but let's just see here. Well, I guess we want to do both. So, carbon has how many electron regions in this structure? 3. So a bond of any order just counts as 1 electron region, right? So when you're counting, if it's a double bond, single bond, you only count it once. Double bond or triple bond, you only count it once, right? So we have 1, 2, 3 electron regions here. So this carbon, unlike our previous examples, now we have these 3 electron regions. So this would just be sp2 hybridized, okay? And again, we got no lone pairs on that central atom, so both the electron geometry and the molecular geometry are the same, and this is what we call trigonal planar. Okay? I'll zoom back out, sorry. The name sort of implies the shape, and you'll see this when we get our hands-on model kit building, but it has these, well, right, it's a triangle, so that's where the trigonal comes from, but it's planar because all of these atoms actually lie in one flat plane. Those molecules are flat on the table, okay? All right, so then let's go back to these same examples here. Well, crap, actually we didn't have one. An example of the next one would be something like, off the top of my head, the only thing I can think of is a nitrite ion. Talk about this here in a second. I know my oxygen breaks my rules. We'll talk about this here in a second, but let's just look at this nitrogen. It has how many electron regions? In a nitrite ion, it has these 3, 1, 2, 3, but now one of them is being taken up by a lone pair, and this is also that very fancy name, bent. All right, and then the last example here that we're going to look at, let's look at our triple bond compound. Let's look at this carbon here. How many electron regions? Just 2, right? I only count that triple bond once. So this is an sp hybridized molecule. And those have both an electron and a molecular geometry that is linear. Those atoms, those 3 atoms sit in a straight line. Okay? So here is a little bit of our cheat sheet chart. If you wanted to take a picture of that, you can. Again, I'll post these lecture slides at the end of the week. But again, just kind of a summary of these different molecular geometries that we're going to see. Okay? So, now, let's go back here. What do we notice about, you're going to trust me, this is an actual Lewis structure for this molecule here. But what do we notice about this particular oxygen on the end here? Right? Does this follow our rules that we laid out earlier? No. All of a sudden we got this different scenario where this oxygen has 1 bond and 3 lone pairs. So what the heck is going on here? This is because the molecule nitrite has a charge associated with it. Okay? So the last thing we're going to talk about today with regard to our structures is this concept of formal charges. Sorry. Cheat sheet here. Cool. Formal charges. And these are going to be really important here. It turns out that chemistry, the most interesting parts of chemistry, usually happen between charged species, right? So these formal charges are going to be a very important part of understanding like why reactions are occurring. We're not there yet, right? We're not talking about reactions yet. We're just sort of laying the groundwork for being able to look at a molecule and understand what's going on. But we need to be able to spy if a particular atom has a formal charge. It's going to be something that's very important, all right? So, more cheat sheet charts here. Okay, and we're going to go element by element here. So oxygen, we're going to make 3 columns. I'll show you why here in a second. Okay. And we're going to keep track of number of bonds, number of lone pairs, and then finally, our formal charge. Okay, so we said oxygen likes to have how many bonds and how many lone pairs? 2. And what we mean when we say it likes to have is that its formal charge when it has 2 bonds and 2 lone pairs is 0. And that is always the most stable state for atoms, right? When their formal charge is 0. Now, reactions don't happen between super stable atoms, right? So when we do have a formal charge, it is less stable, but we're going to see it a lot, and those tend to be the more interesting compounds. So, how did I know in that molecule that I had a formal charge of -1 on that oxygen? Because I had only 1 bond, right? Decreased the number of bonds, and it increased the number of lone pairs. So that molecule that I drew had a formal charge of -1 on that oxygen, and I knew it because it only had 1 bond and 3 lone pairs on that oxygen, right? So that would be an oxygen with a negative charge. Let's actually go ahead and draw examples up here. So that would be 1 bond and 3 lone pairs. Boom. Okay. And now they tend to be more rare. You don't see them quite as much, but there is an oxygen with a positive formal charge. And let's just see if we can't spy a pattern here. If I went down in number of bonds to get a negative formal charge, what am I going to do to get a positive formal charge? More bonds, right? So oxygen will have 3 bonds and only 1 lone pair if it has that formal charge of +1. Notice each bond is 2 electrons, right? Each lone pair is 2 electrons. So in every case here, how many electrons is associated with my oxygen atom? That's full octet, right? It still has its full octet. All I've done is swap bonds for lone pairs. Okay? All right, so now let's do our other one that we're going to see a bunch with formal charges. and that is nitrogen. All right, so again, nitrogen, we say it likes to have how many bonds? According to our cheat sheet, 3. And it likes to have one lone pair. When we say that, that's because it has a formal charge of 0 when it has 1 bond, and, or, I'm sorry, 3 bonds and 1 lone pair. All right, so that's nitrogen in its happiest form right there. Let's see if we can't use what we just did before and infer how many bonds it would need if it had a formal charge of -1. What am I going to do? Go up in bonds or down in bonds? Look at what we did for oxygen. We're going to go down in bonds. So nitrogen would have 2 bonds and up in lone pairs. All right? And just think about that. Why does going up in lone pairs increase your negative charge? Well, lone pairs are electrons that sit only on that atom, whereas bonds are electrons that are being shared, right? So some of that electron density is over there with the other atom in a bond. All right, so if we have 2 bonds and 2 lone pairs, that is nitrogen with that negative charge. All right, and then who can guess how many bonds for a formal charge of +1? 4 bonds. And how many lone pairs? None. And this we actually see quite often in organic chemistry, a nitrogen with a positive charge like that, formal charge of +1. Okay? And in each of these 3 scenarios, how many electrons are in that octet? All 8, right? So even though they're adopting this formal charge, we still never break the octet rule for nitrogen and oxygen. It just never happens. All right, and now we're going to do the organic chemistry star, carbon. We say that carbon likes to have how many bonds? 4. And how many lone pairs? 0. Whoa, just jumped. And we say it likes to because then it has a formal charge of 0. What about if it has a formal charge of -1? I guess I kind of just gave it away. How many bonds do we think? We're going to go down in bonds and up in lone pairs here. Okay? We have a special name for these when it's carbon. This is called a carbanion. Right? Anions are negatively charged ions. A carbanion is when carbon has a negative charge. They are super duper unstable. Carbon is super mad right now if it has that negative charge. All right, now let's talk about a formal charge of +1. Okay? And this is going to be the exception to sort of this rule that we've been holding up until now. I can't have 5 bonds with my carbon, right? So I can't just increase the number of bonds. It turns out that a carbon with a positive charge has 3 bonds and no lone pairs. Okay? This is got a fancy name as well. This is called a carbocation. Because it's a cation, it's got a positive charge. But notice that this is the one example that we've seen here where the octet rule is actually broken for this molecule, right? A carbanion has an incomplete octet. We're going to see that these are actually very common intermediates in organic chemistry reactions, but they're very unstable. They only exist for a small amount of time at a second because that carbon's really mad, okay? But notice that this is sort of our octet rule exception. Let's just make a note of that. Cool. All right. Okay, so let's say that I gave you an incomplete Lewis structure. All right? I give you something that looks like this. Okay? Everybody go ahead and copy this structure down, because then you're going to be adding to this here. You're going to need to complete my drawing for me by adding in any missing lone pairs and formal charges. All right, so all my bonding electrons have been drawn, but I'm missing lone pairs here. How many lone pairs should I be putting on that oxygen? Yes, because it only has one bond, right? So if it only has one bond, I got to make up the rest of that octet with those 1, 2, 3 lone pairs, which means that that oxygen has a formal charge of -1, right? So we would just put a little minus sign. Sometimes there's a circle around it, sometimes not. I don't remember what I do now. I'm probably going to do it both ways throughout the course of the course, but yes. So, and this is kind of important to be able to just see what we're sort of building towards here is, again, we're going to simplify things, or rather get a little bit lazy with our structure drawing. And at some point, you'll get to an advanced portion of organic chemistry where they stop drawing the lone pairs of electrons. Everybody knows they're there, and they just get kind of lazy. And so when, like in more advanced parts of the course, these lone pairs are going to be implied. We're going to know that they're there because oxygen has one bond. It has to have those 3 lone pairs, right? For now, we're going to work on this sort of thing where you fill them in on these structures, right? So that you know that they're there, so you can practice knowing that they're there. All right, so let's do another one. How many lone pairs on that nitrogen? Just 1, and if it has 3 bonds and 1 lone pair, it's got a formal charge of 0, right? So if it is 0, we don't bother annotating it at all. We just leave it like that. What about my oxygen? How many lone pairs? It's going to need 1 because it's got 3 bonds associated with it. So we're going to have to put just 1 lone pair on there. And if it's got those 3 bonds and 1 lone pair, it's got a formal charge of +1. Okay, so now let's roll together a bunch of stuff that we've been talking about here. I'm going to look at this nitrogen, and you're going to tell me what its hybridization is and what its geometry is. The molecular geometry, we'll say. What's that hybridization? sp3. It's got those 4 electron regions. And then what about the molecular geometry? So first of all, the electron geometry for everything that's sp3 is tetrahedral. But what's the molecular geometry when I have that one lone pair? Trigonal pyramidal, okay? And so again, we'll sort of be working with these structures, and it'll be helpful to sort of drill this into your head. But these are going to sit off the table a little bit as opposed to trigonal planar, which will be flat, right? So this is trigonal pyramidal. All right, and then I want you to do the same thing, but you're going to do it for this carbon right here in our structure. Okay, again, tell me the hybridization and the molecular geometry of that carbon. All right, and then lastly, and we'll do these two at the same time, but if you're done with that one, you could do that middle carbon as well. We're going to do all 3 of these in our backbone here. I guess we'll do them in order. Let's do this blue one first. What's the hybridization? sp3. It's also got those 4 electron regions. And then what would be the geometry of that carbon? Tetrahedral, yep. With no lone pairs, the electron geometry and the molecular geometry are the same. Tetrahedral. Okay, and then lastly, that green carbon, what's the hybridization?
sp2.
That one's just sp2. And sp2 with no lone pairs is going to have a molecular geometry trigonal planar. So our other trigonal, but this one is trigonal planar. All right. And so notice that for these molecules, for any sort of large molecule, they don't just have like a one name geometry, right? You got to look about each one of these atoms. Every single one of these atoms that we highlighted had a different geometry associated with it. So unlike what you were sort of told in general chemistry where you had one word for the molecule, that works great for very simple things. For things that are more complicated, you got to go down the line and specify. Okay? Let's just do one more with our time that we got left here. Actually, we'll put everything together here. You will draw me the structure of something with the formula C2H8N. Right? And if you get one structure, there are quite a few with this same formula. See if you can get a second one that's different from your original structure. All right, and then I also want to know the hybridization and the geometry of that nitrogen in your structure. So if I put my carbons and then my nitrogen, and I start filling these in with hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. I could see in my formula here that there's a formal charge of +1. Which atom does that formal charge live on? That nitrogen, and I can spy that because it's got those 4 bonds, right? So that's my formal charge. How many lone pairs should I be putting on that nitrogen? None, right? 4 bonds and 0 lone pairs are our bonding pattern. The other way you could have done this is to put the nitrogen in the middle. In both cases, it would have had 4 bonds and no lone pairs. So again, regardless of which structure you looked at, you would have that positive formal charge on your nitrogen. Okay? And then we said we're going to look at this nitrogen, and it really doesn't matter which one you pick, and we're going to figure out what its hybridization is. What's the hybridization on that nitrogen? sp3. And what is its geometry? Tetrahedral. All right, cool. So we're going to stop there. That is pretty much exactly what I wanted to make sure to get to today. I will say that starting tomorrow, or not tomorrow, I guess, Wednesday, we're going to work on taking these Lewis structures, which are such a pain in the butt to draw. And we're going to learn how to draw what is a way more simplified structure, which is called a bond line structure. And those two are the same thing, right? So we're going to learn a little bit of a shorthand for how we draw structures. And I'm super excited to teach you all that because then we get to use it throughout the rest of the course and we don't have to draw these long friggin' Lewis structures here, okay? It conveys the same piece of information. We'll talk about how I go about reading these next class, all right? I'm going to take attendance, and if you have any questions, you can come up and ask me at the end here.